We're glad you clicked on this video to join us for the next part of the 17th chapter. In this part, we'll be discussing the control of various electric motors.
Electric motors are one of the most common tools in our everyday lives, but without proper control, they would be useless. For a given task, it's important to consider what you want to use the motor for, as there may be applications where you do not need a control circuit built in. For example, in the case of a simple household or kitchen appliance, this can almost invariably be left out, as the mains voltage is a 50 Hz sine wave, which is perfectly suitable for powering asynchronous motors or universal motors, in which case the mains will provide the appropriate control. Of course, the developer has to take care of the starting problem, for which we have already discussed the most common methods in the previous video. Direct feeding saves the cost of the motor controller and makes the device much simpler. However, we can be sure that in engineering, we cannot get away with using a motor controller when we need precise control.
In the case of DC motors, with mechanical commutation, the current drawn by the motor is proportional to the rotor torque and the supply voltage is proportional to the rotor speed. Thus, if I want to change the speed of the motor, I have to change the magnitude of the voltage applied to it. You can see an example of this in the video in Chapter 13 of the Crystal Clear Electronics 1 curriculum. If you switch the motor's supply voltage on and off fast enough, the motor will only rotate at the speed corresponding to the average value of the square wave voltage applied to it, because it doesn't have time to follow the fast switching. This is basically the equivalent of a PWM control.
The alternating current motors are driven by sine waveform current, and for both asynchronous and synchronous machines, the speed of rotation is determined by the frequency of the sine wave. The breakthrough in the application of AC machines has been the development of semiconductor technology. It then opened the way for engineers to create a sine waveform of any frequency at low cost, without mechanical components. This can also be implemented with PWM.
After this brief introduction, let's look at the main components that make up a motor controller.
This figure shows a general motor controller block diagram. The dashed line indicates the boundary of the motor controller. Although the sensor that senses the rotation of the motor, the encoder, is located on the motor shaft, it is logically part of the controller, not the motor. Without it, the closed control loop could not be implemented. Eagle-eyed video viewers may have noticed that I have used the term closed loop controller. This is not by mistake. Controls, where there is feedback in the system, meaning we measure the physical quantity that we want to control, are called closed loop controls. Controls without feedback are called open loop controls. In everyday conversation, we don't always emphasize whether we are talking about open or closed loop control. The term motor controller has become a common phrase. From just that, we don't know if we are talking about a closed loop control, where we are using the speed signal provided by the sensor, or an open loop control, where we don't. The sensor that detects the rotation of the motor is called an encoder. They can be basically divided into two groups, incremental and absolute encoders. The most common incremental encoders are mechanical, optical, or magnetic. In this chapter, we will only deal with the magnetic ones, as this is the principle of the encoder on the DC motor next to me, which we will use in the next video. However, it's important to note that the type of the encoder does not affect the principle of operation. For all three types, the determination of the rotation is based on the counting of pulses. The only difference is what triggers these voltage pulses. In the present case, the Hall effect sensors detect the rotation of the magnetic disk and, depending on its position, emit 16 pulses over a complete revolution, meaning one every 22.5 degrees. By counting these and measuring the time between them, the rotation speed can be easily calculated.
However, with a single Hall effect sensor, we cannot determine in which direction our motor is rotating, which is why two sensor encoders have become widespread. Their sensors are located at some angular rotation distance from each other. This distance depends on how many pulses the encoder emits in a single revolution.
In the present case, these Hall sensors are about 100 degrees apart. Thus, due to the rotation, the pulses will appear with an offset at the output of the A and B channels of the encoder. Depending on which channel the pulse hits first, we can determine the direction of rotation. With single and dual output encoders, we only have information about the relative rotation. We don't know the position of the motor's shaft when it is switched on, only how much it has rotated relative to it. To solve this problem, 3 sensor incremental encoders have been developed. In these, the third sensor pulses only at a single position during the entire rotation, giving the absolute position of the shaft. The channels of the encoders provide us with square wave signals from which we determine the rotation. Note that so far we have only considered the rising edge of each level change, but if we also considered the falling edge, we would have twice as much information and would know the position of the axis with twice the accuracy. In the case of single channel encoders, we can consider only one or both edge changes, and in the case of dual channel encoders, we can do the same for both signals, which can be referred to as single, double, or quadruple evaluation. In the case of 3-channel encoders, the third channel does not operate in the same way as the other 2 channels, but only produces one pair of edge changes per revolution, so evaluating the third channel does not provide any additional information in this respect, and therefore does not increase the accuracy of the evaluation. The simpler, and therefore cheaper encoders contain only one channel, so they are less accurate than their 2-channel counterparts. Depending on the precision required, a single channel encoder with a single evaluation may be sufficient, and is the simplest solution, which is cheaper from a hardware point of view and less computationally demanding from a software point of view. The accuracy can be increased by double evaluation, but this requires more resources on the part of the microcontroller. Note that a single channel encoder with double evaluation provides exactly as much information as a dual channel encoder with single evaluation.
Many microcontrollers have interfaces for processing incremental encoder signals. It is discussed in more detail in Chapter 15 of the Crystal Clear Electronics 2 curriculum.
Absolute encoders are designed to overcome the drawbacks of incremental encoders by eliminating the need to count and store the output pulses for determining the magnitude of displacement or position using an external counter. Absolute rotary encoders are designed to read the current position at any instant. The principle of operation of these encoders can be classified as mechanical, optical, magnetic, inductive, which is also known as a resolver, and potentiometric. We will not go into the details of how they work.
The signal shape needed to drive the motor is provided by the microcontroller, but for now keep in mind that its output stage is only capable of providing a small amount of power, which is not enough to drive the motor.
As we've already mentioned, one of the most common solutions for controlling the speed of brushed DC motors is the PWM. The essence of the PWM method is to generate a constant frequency square wave signal whose duty cycle is varied as a function of the desired speed. This PWM signal is amplified by a power stage to the appropriate level for the motor. If the resulting signal is passed through a filter circuit, we obtain the average of the signal, which is effectively a DC voltage, the appropriate signal shape for a DC motor. Most microcontrollers have a PWM output, so it's obvious to use this. But you can also generate your PWM signal with a circuit of discrete components. Let's first examine the half-bridge circuit shown in this figure. L and C2 form the filter used to smooth the output voltage, and there's also a supply voltage source U in, an input filter capacitor C1, and a load resistor R load, which in this case is used to replace the motor. If switch 1 is on and switch 2 is off, voltage U in can be measured between P and ground. In the opposite case, it is 0 volts. Care should be taken not to turn on switch 1 and 2 at the same time, as this will short-circuit the voltage source through the switches. Then, a short circuit will flow, which usually destroys the circuit. To avoid such situations, an IC designed to drive a half bridge should be used to control the switches. Imagine such an IC connected to switches 1 and 2. If this is controlled by a PWM signal, a voltage proportional to the width of the pulse will appear across resistor R load, with a maximum value of U in and a minimum value of 0 volts. With proper considerations, a DC motor with mechanical commutation, so one with a permanent magnet, can be connected directly to point P. The motor's coil, by its physical design, acts as a filter. Consider what happens if you suddenly apply voltage to the motor. The motor currently cannot rise infinitely fast because the motor's coil has inductivity, which means that the speed at which the current can rise is limited by self-induction. It's very important that the PWM frequency is set high enough when using this type of circuit, otherwise the motor torque will pulsate significantly due to the pulsing current.
With a half-bridge connection, you can only turn the motor in one direction because you can only create a positive average voltage on the terminals. If you want to operate your motor in both directions, you should use the full bridge, or also known as H-bridge circuit.
In the so-called bipolar control of the circuit shown in the figure, two switches must be switched simultaneously. If switch 1 and switch 4 are switched on, the voltage between P1 and P2 is equal to U in. If, on the other hand, switches 2 and 3 are closed, then it equals minus U in. We have to be careful not to turn on switch 1 and 2 or switch 3 and 4 at the same time, because then we will short-circuit our power supply and the high current will destroy the circuit again. As with the half-bridge circuit, there are of course driver ICs for the H-bridge circuits that will ensure that this does not happen. If a high signal is applied to the input of such an IC, then switches 1 and 4 are turned on. If a low signal is applied, then switches 2 and 3 are turned on. In this case, the average of the motor output voltage for a switching period can be adjusted proportionally between minus U in and plus U in, depending on the pulse width. 0% duty cycle will give minus U in, 50% will give 0 volts, and 100% will give U in. Half-bridge and full-bridge circuits are commonly used to drive DC motors. For three-phase motors, we need the so-called three-phase bridge circuit, which is actually 3 half-bridges whose outputs are connected to the three-phase lines of the motor. The detailed operation of this circuit will not be discussed here. Still, it's essential to know that by varying the output voltage of each half-bridge sinusoidally, and by shifting the output voltage of each half-bridge by 120 degrees relative to one another, the motor can be rotated.
So far, we've learned about the principle of the power stage and how it is driven. We have not yet discussed what real physical components should be used as switches.
The range of these components is very wide, and the optimal choice will be influenced by the motor power and voltage level, and whether or not it will be controlled by a PWM signal. The wrong choice of component can lead to heating in the best case, or in the worst case, to burnout and malfunction. Typically, MOSFETs are used at lower voltages and currents, but higher switching frequencies, while IGBTs are used at higher voltages and currents, but lower switching frequencies. MOSFETs have already been discussed in Chapter 7 of the Crystal Clear Electronics 1 curriculum. The abbreviation IGBT comes from the English term insulated gate bipolar transistor. What's worth knowing about it is that it is very similar to a MOSFET in terms of its control. It has a gate, but in terms of its output, it's more similar to a bipolar transistor. It has a collector and an emitter. Due to its construction, it has a higher switching loss than MOSFETs, but in return, you can buy devices that can handle thousands of amps and thousands of volts. Integrated solutions are also available where a half bridge, H bridge, or three-phase bridge is placed in a package. These are the devices in front of me. For example, this is an IGBT half bridge, this is an IGBT full bridge, this is a three-phase bridge with MOSFETs, and it's the odd one out, or not really, but the left out element is this IGBT three-phase bridge. For all types, it's advisable to use some kind of driver circuit to control the gate electrodes for fast and smooth switching.
It is also worth mentioning that nowadays silicon carbide and gallium nitride MOSFETs are also becoming more and more common, which have several advantages. Typically, they have lower switching losses, allowing better efficiency or smaller devices to be made.
In addition, there are integrated solutions where the driver IC includes the MOSFET itself. The development panel for Crystal Clear Electronics 2 also includes an IC with a complete H bridge in the case. The datasheets for both the driver and the ICs, containing the switches invariably, explain how they must be controlled to obtain the correct output signal shape. On this basis, a distinction is made between components that can be controlled by analog, digital, and PWM methods. Analog controllable components also provide PWM signal at their output, in which case the duty cycle of the output PWM signal will be directly proportional to the input analog signal level. In other words, if the input voltage is applied 2 times and then 3 times as high, the output will have a signal with the duty cycle 2 times and then 3 times as high. Of course, the maximum input voltage must be taken into account, which can also be read from the datasheet. This value corresponds to the maximum duty cycle PWM signal, which for most ICs means 100%. There are also components that have a digital communication channel that can be used to tell what output signal shape you want to see on a particular interface, for example, I2C, SPI, or UART. The third group of ICs allow the developers to generate the PWM signal themselves and generate a square wave signal with the same duty cycle and frequency as the input PWM signal at their output.
There are ICs available on the market that can be controlled in more than one way. In the following, we will use an L298 IC-based driver board to control a DC motor that only needs a PWM signal to operate. We will show how we can implement it in the upcoming video. Stay tuned.
Bye.